Eastview Scholars, and welcome from Normal, Illinois in the Sweet Corn Blues Festival. All those people you see behind me are buying the greatest sweet corn you've ever had out of the farm fields of Illinois. There's a lot of blues, there's a lot of music, and it's a great time. Whenever I see this sea of humanity and I see all this delicious corn and the nutrients and everything else, I start thinking science. So we're going to talk some science, but right now I'm going to go catch some tunes at the Blues Fest. I look at all these plants, I look at people eating these foods, I look at all the metabolism going on in these cells, and I start thinking AP Bio all the time.
Hello, Eastview Scholars. I am back from the Sweet Corn Blues Festival in Normal, Illinois. It was a great day, a lot of corn being sold. There was more people actually before I was filming, but then a big thunderstorm rolled through and we had to duck and cover. Anyhow, on this edition of Sharp Shorts, we are going to run through quickly the basics of the chemical context of life, or in other words, all that chemistry I took last year, how does that apply to living organisms? Okay? One of the things to learn in biology is the cell is the smallest functional unit of a living organism. As you learned in chemistry, the atom is the smallest functional unit of matter. And so we're not going to spend a lot of time here. A lot of you should have had your chemistry, your honors chemistry requirement for taking this course. But we do want to run through a few things, because as we see throughout this course and as we go, as things go from the simplest hierarchy of the atom to the molecule and on up to the cell and to the organism, at different levels you have different emerging properties. And so that will be a theme throughout as to how do things change as they become more complex. As you can see on the quote here, the majority of the atoms in your body come down to four. 96% of everything you are is hydrogen, oxygen, carbon, and nitrogen, and then little bits of everything else. And that's a little quote from our friend Bill Bryson, who has a great book, A Short History of Nearly Everything. Okay, so here we go. Here's what we're most concerned with. CHNOPS, we call them. The carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Of course, carbon, hydrogen, nitrogen, and oxygen are the main ones. Phosphorus, sulfur, sodium, potassium, calcium, magnesium, chlorine, and other trace elements are that small non-96% that cover things. Quick chemistry question: are the elements or compounds? You should have answered by now. Okay? And also, reading the square on the periodic table, there's the one for sodium. What is the atomic number? You should know that that is 11. And what does it tell you? The number of protons. And by assumption, we'll leave it out there. You know by assumption, but you have to be careful. What is the mass number? There it is. It's about 23. What does that tell me? It tells me the number of protons and neutrons. This should all be a reminder. So, there we go. How do I know this is sodium and not some other element? Because it's defined by its protons, correct? I hope so. What do the signs represent? The negative signs there represent electrons. How can we predict the number of electrons in an atom? Well, if the atomic number is the number of protons, and in theory a neutral atom is neutral, then the atomic number and the proton number and the electron number are all the same. Again, that's an assumption because it can form an ion. What is the charge on a proton and a neutron? I hope you've answered that in your head already. So, here's what I'm going to say. Here are the basic parts of the atom. If I change the number of protons, what happens? Actually, I can't. That changes the element. When you have proton decay, that happens with radioactive elements. If I change the number of neutrons, I have an isotope of that element, which is just a different form, which can be very important in living organisms, as with iron, for binding and releasing oxygen in hemoglobin. Change the number of electrons, I've got an ion, U. So here we go. Electron configuration helps you identify the number of valence electrons, because that's the one that helps you understand bonding and reactivity and what it's doing. Oh, there we go. So there is, sorry, went a little quick there. There is your sodium, 11 protons, 12 neutrons. Here we have one that has 10 neutrons, 10 protons, and it looks like we're all neutral in our valence shell. That's a noble gas neon. Full valence orbital like all the noble gases, so they are non-reactive. Reminder again. So let's go back to bonds. What types of bonds do we have? We have covalent bonding. That's the sharing. That's the easiest way that people say it. It's sharing their valence electrons. More bonds they share, the less flexible the molecule is. Again, one of those properties that will come up later is how does that then affect the organism as a whole as the hierarchy kicks up. Just because they share electrons doesn't mean they share equally. Remember that electronegativity of how much something wants to grab an electron. So, attraction of an atom for the electrons in a covalent bond is an easy way to say it, kind of like when a really popular person such as myself gets to the party, you can see before I get there and after I get there the attraction that I have for most folks. Okay. On a relative scale, you can see that oxygen is more electronegative than nitrogen. Carbon and hydrogen are about the same. Anyhow, the point of that, with our friend water here and the covalent bonding, is that you see there's the covalent bond sharing the electrons. Certainly the oxygen is more electronegative, has a stronger nucleus, stronger pull, so you're going to create these dipole moments, which then make water polar because the hydrogen end is slightly positive, the oxygen end has a negativity to it, and that makes it a polar covalent bond. Polar covalence, unequal sharing, okay, more to less electronegative, so those are polar. Non-polar covalent bonds, carbon and hydrogen, are about equal. Your diatomics are exactly equal, so those would be non-polar. And key solution chemistry, you remember here, because I hate to tell you this, as a living organism you are one big bag of chemical reactions. Like dissolves like. So polar substances dissolve in polar solvents, water. Non-polar substances dissolve in non-polar, ether. Okay. And then ionic bonds. Ionic bonds, the electronegativity difference is so great, essentially you have a transfer of one electron to another, it just leaves, and then you can create either a cation or an anion, and that positive and negative then causes that electrostatic charge. Okay. So, ionic bonds very strong in dry environments, but weaken in water. Why? Because water is polar, even though it's a covalent bond, it's a polar substance, so it dissolves and breaks those bonds. Molecules themselves also can have weak interactions. Here is an example. We're not going to go through all the ones you went in chemistry, but here is an example of a hydrogen bond. The dipole moment, the positive portion of the hydrogen there in the molecule, the dipole positive side, is attracted to the negative side, so you get a little intermolecular. And again, emerging properties, how does that change things as we get the hierarchy together? What does that do for the structure of water, or what does that do in your body, because you are, you know, 2/3 water anyhow? That's a good question. So the hydrogen bonds attracted to one another, to one electron is attracted to the oxygen in another. Okay. Van der Waals interactions, even non-polar substances can have attractions because those electrons are moving around so rapidly. They're not always evenly distributed, so you can have these very weak forces where you have these momentary dipoles because you have this flying around electrons, flying around, probably not the best term, but you have the constant movement of the electrons creating dipoles, and if you gather a bunch of them together, you can have weak interactions, which is why geckos can crawl up walls. That'll do it for our quick run through. We'll talk a little bit more about this in class to make sure you get the concepts and stuff, but there's your quick run through. Scholar up, Eastview.